Alright, so today we're going to continue practicing, basically. So we want to further practice infinite limits and understanding graphs of functions and their derivatives. So first, on the accompanying sheet that I gave you today, I want you to do the 8 example graphs. There are many correct answers for them, but I want you to come up with at least one graph for each, and also then think about, if you don't graph them, at least think about other scenarios for what types of graphs would have those limits. So pause the video, do those 8 graphs, unpause when you're ready to discuss. And by discuss, as usual, I mean listen to me talk. Alright, so here are 2 examples for number 1. The limit as x goes to 2 of f of x equals -1. So one thing would be if the function exists at the point 2, -1, and it is continuous at 2, -1. So that's my example here. There are much simpler or more complex versions of that. Or if there's a hole, but the function is continuous to the left and the right of the hole, so the limit as x goes to 2 is still going to be -1 if the hole exists at the point 2, -1. So these are 2 examples. There are many other correct examples. Here, what is the limit as x goes to infinity of f of x equals infinity. So an exponential function would be an example of that. Quadratic would be an example of that. Some sort of rational function with a slant asymptote would be an example of that if the slant asymptote has a positive slope. Or some other sort of oblique asymptote. So again, here there are many correct answers. These are just a few of them. Here, the limit as x goes to infinity of f of x equals 3. So if we have a horizontal asymptote at 3, so if you have a rational function with a horizontal asymptote at 3, or if you have, for instance, exponential decay, but we have a vertical shift of 3. So that's another example. Again, there are many correct solutions. The limit as x goes to -infinity of f of x equals 2. So here this would be exponential growth, but with a vertical shift of 2. Or again, you could have a rational function with a horizontal asymptote of 2. The limit as x goes to -infinity of f of x equals 0. So our standard exponential growth function has that property. Again, a rational function now with a horizontal asymptote of 0 would also have that property. The limit as f of x, the limit as x goes to infinity of f of x equals -infinity. So here I did a rational function with an oblique asymptote that's going down as x goes to infinity. This would have a negative slope. Or you could do this is an exponential function, but with a reflection over the y-axis. Over the x-axis. So we would multiply the y values by -1. So as x goes to infinity, f of x goes to -infinity. Again, these are just examples. There are many correct solutions. Here we have the limit as x goes to 2 from the right of f of x equals -infinity. So here you need to have a vertical asymptote at x equals 2. So I did a rational function with a vertical asymptote at x equals 2, and as I approach 2 from the right, the function is going down to, the function is going down to -infinity. I also did an example of a log function. So for instance, I actually wrote it down this time, but y equals the natural log of x minus 2. So this is a log, or the natural log function shifted 2 to the right, but you could do any log function shifted 2 to the right. And then the last one, the limit as x goes to 2 from the left. So I actually just copy and pasted the same exact image that I did on the previous one, because here as I went to 2 from the right, I went to -infinity, but as I went to 2 from the left, I went to positive infinity. So again, if I have a vertical asymptote at 2. And then this is a log function, but with a reflection in both the x and y axis, as well as a shift. So as we approach 2 from the left, the function is going to positive infinity. Alright, now I want you to do the AP problem on the back of that sheet that I gave you. So I want you to pause the video, use the information given, and for axes between 0 and 4, find all values of x at which f has a relative extremum. Determine whether f has a relative maximum or relative minimum at each of these values. Justify your answer. And then part B, there is no axis provided, so you're going to have to provide your own axis. I take that back, I apologize. I forgot that I put an axis on your sheet. That's because I spoil you and I treat you so well. I was nice enough to put an axis there. So anyway, on the axis provided, sketch the graph of a function that has all of the characteristics of f. There are, again, many correct answers. So pause the video, solve that problem, unpause when you're ready to check your work. Alright, so for part A, there is only one relative extremum, and that is going to be at an x value of 2, or at the point 2, 2. So that's actually what I should, so that, sorry, don't mind me. So f prime of x, and we want to answer this in derivative speak, remember, we're very formal. F prime of x is greater than 0 on the interval 1 to 2, and f prime of x is less than 0 on the interval 2 to 3, so at the point 2, 2 is a relative maximum. Notice that here we could not use the second derivative test because the second derivative does not exist at 2. So we had to use our first derivative test. There are no other maximums or minimums because there are no other changes from positive to negative for the first derivative. Alright, so now looking at a possible graph, well, we know some points. We know the point 0, negative 1. We know the point 1, 0. We know the point 2, 2. And we know the point 3, 0. We don't know where it is at 4. But we do know that the function is negative and that it's decreasing because the derivative is also negative. And we know that it is concave up because the second derivative is positive. So we know that at the point 1, 0 and at the point 2, 2 and at the point 3, 0, concavity is going to change at all three of those points. So from 0 to 1, the function is concave down. From 1 to 2, the function is concave up. From 2 to 3, the function is concave down. And from 3 to 4, the function is concave up. And so that's why we have this weird kind of turn here at the point 2, 2, where the first derivative and the second derivative do not exist, because that's a sharp turn. Alright, all good stuff. So now I want you to find the limit as x goes to infinity of the function 2x squared minus 4x over x plus 1. Pause the video, unpause when you're ready to check your work. Okay, so we should end up with the limit as x goes to infinity of 2x squared minus 4x over x plus 1 is infinity. So how do I come up with that if you're not sure? Well, what I did here was I recognized this is a rational function. It is going to have a slant asymptote because the degree of the numerator is 1 greater than the degree of the denominator. Therefore, I found the slant asymptote because remember, the slant asymptote is going to predict the end behavior. So in this case, I chose to do synthetic division. You could have done long division as well. So I did synthetic division, and I ended up with the slant asymptote as the function y equals 2x minus 6. Remember, when we're doing the synthetic division to find a slant asymptote, we don't care about the remainder. So as soon as I got to the remainder stage, I stopped the synthetic division. So the slant asymptote is the line y equals 2x minus 6, which has a positive slope. And I know the limit as x goes to infinity of 2x minus 6 is infinity. And since this is the function that predicts the end behavior of our rational function, this is also going to be infinity. Okay, last example. So if we have this vase here, and water is running into the vase at a constant rate, I want you to try to sketch a graph of the depth d of the water in the vase as a function of time. Does the function have any extrema? And interpret the inflection points of the graph of d. So pause the video, try to sketch that graph. So you're trying to sketch depth with respect to time, and talk about the extrema and the inflection points. Unpause when you're ready to check your work. Okay, so the function d with respect to time should look something like this. Obviously, the volume is 0, or the depth, I'm sorry, is 0 when time is 0. And then the inflection points are the widest and narrowest point on the vase. So we'll talk about those in part C in a second. There are no relative extrema since the derivative is always positive because water is always flowing into it. So there are no relative extrema. So the rate of change of D is decreasing until it gets to its widest point. That's why it's concave down. Then it is increasing until its narrowest point, and so that's when it changes to concave up. And then it is decreasing again until you reach the top and the vase is full. Alright, so in conclusion, really make sure we know the relationship between a function and its derivative inside and out. It's really important. Have a good night.